Hi everyone, and welcome to today's session. Today we are talking about an exciting new paper named CRADLE. So this was developed by some researchers in China as well as NTU. And what they did was that they used large language model plus a bit of video image processing to basically play this game called Red Dead Redemption 2. So for those who don't know, Red Dead Redemption 2 is like more like an open world kind of concept where you need to fulfill quests and so on. So this is actually quite difficult for like AI systems to do because you need to understand how to interact with the world and so on. So how did they do this? So let's just take a look at how this paper did it and how we can use some of the lessons they learned there to build better systems. Okay, so this is not a great model yet. It's good for some tasks. It doesn't solve the whole game, but there's some lessons that they learn and they're quite open to share about this in the paper. And we can use this to improve on such a cognitive system that could play like better video games and hopefully even be applied to the real world. All right, so let's take a look at the video. Okay, so I'm going to show you their video first, first half a minute of their video, and then we will continue with the rest of the presentation. Can you see the slide? This one, this is the video. Okay, all good. You can just put your thumbs up.
Yes, we can see.
Okay, let's I'll just play you the first half a minute, and let's take a look.
Computing devices are the common interface in the increasingly digital world and cover a wide variety of scenarios. While promising, AI agents still haven't unlocked their potential to assist users across such tasks. Here we showcase CRADLE, a novel agent framework playing the complex Red Dead Redemption 2 game to illustrate its capabilities in a challenging setting. CRADLE is capable of understanding dynamic visual information, learning new skills, self-adaptation, and accomplishing tasks through only standard observation like screen images and input device operations.
Okay, so you can see in this game, it is quite open world. You see there's some subtitles, there's the weapon wheel and so on. You need to do some kind of fighting and so on. So to do this game properly, you need to do quite a lot of skills. Okay, so all right, so let's go back to the slide. Okay, so just one thing to note, CRADLE does not play this game like humans do. Because of the latency of the image processing, it actually plays it about 20 times slower than humans. So that video that you just saw was sped up 20 times. So in reality, what will happen is the character will just stand still, and then GPT will process at the back end. And then once they process, then they'll map back some actions to the game, and then the executor will then execute those actions in the game. So it is still not there yet. Okay, so if you were to play first-person shooter with this AI, you will definitely win. Okay, because they will take quite some time to even target you and aim at you. So, but putting all this aside, how did they manage to play the game? Okay, and this game playing is not easy because it requires you to understand the image of the world, understand what are the instructions given by the game. So, firstly, let's go with the broad aim that the authors of this paper want to achieve. So what they want to do is this thing called general computer control. Okay, so this Red Dead Redemption 2 is just one way to showcase what the system can do, but the more broader aim and the higher objective is basically to create an interface. Okay, and this interface is basically this this box over here you can see here. Create an interface like this. Okay, that once you get a visual input from, let's say, a computer or device, it can be a smartphone, it can be a laptop, it could be a desktop, or other future like VR systems or so on. So you get input information from your device. You gather some information that you need from your input source, like what are the pictures available, what are some of the objects, what are some of the text that you have. You reflect on what you see, and then like, what am I supposed to do? What task am I supposed to do? What is shown in the screen? Has my previous task succeeded and so on? Then you infer, okay, what should I do now? Okay, you infer what is your next task. Okay, so I like this a lot because I believe that humans are also goal directed or task directed. You can see that in task gen, the one I talked about last week. That we just try to make an agent execute a task, and I think this is more or less the way that humans work. Okay, so some people might disagree, but having an objective is quite important for making decisions and planning, because with that higher objective in mind, okay, then you can choose, okay, what to do. And what to do, I like this a lot, okay, this skill curation. Okay, you don't just feed in all the possible actions or functions to the agent. You just feed in those that are relevant to what the agent decides to do here based on the task. Okay, so it's very similar to the task framework. Also, you curate some of the functions based on like cosine similarity and so on, to match the tasks. So with this subset of tasks, subset of skills, you are able to then form a more like, you are able to explore within this subset to find out what to do. So action planning is basically if you have some form of like world model of the world, you can like plan ahead, see what your actions would give you. You know, this is the half part. Okay, this one even TaskGen also doesn't have yet. Okay? But this action planning is difficult because in the real world, like your actions may not have like the same kind of outcome as per all the time. Okay, sometimes it depends based on the context and so on. So we can do action planning pretty well for games like Go. Okay, but in the real world, if you want to do the same action, like walk forward, you know, or move your leg, like maybe 90% of the time you move forward, but 10% of the time maybe you can't because you get stuck on something. So this action planning, this is let me just highlight this part. This is unsolved due to complexities of the real world. Okay, but do you really need to solve this to do most tasks? Not really. Most tasks, you know, if I want to move forward, I can just assume that I'll be moving forward. If something went wrong, I can just reassess again. Okay. So in general, this whole cycle of gathering information, reflection, task inference, curating your skills, doing some action planning, this whole thing is like a cognitive chain. Okay. Basically, you get your input stimuli, you decide what you want to do, and then you do it. And after that, you know, you observe the world. There's one loop here. You observe you take the action in the world. And then what you do next is that it's actually not just a one-way trip. Okay, this is more like a reinforcement learning kind of thing, where, you know, you go back here. Okay, you have next observation of the world. Okay, which you can then use to, you know, reflect on whether you did your action successfully and so on. Okay, I use reinforcement learning here loosely. Okay, because rewards are not scalar. Okay, the rewards over here, in fact, there's no rewards. It is just based on observation. Choose tasks, choose skills. So it's more like a kind of matching, pattern matching, that based on observation to the desired selection. So I like this a lot because, you know, I don't know if you all have done reinforcement learning before, but I've spent 4 years of my PhD doing reinforcement learning, and I realized that reinforcement learning will not get us anywhere close to artificial general intelligence or anything of that sort. What it can do is it can get us very close to playing perfect games, like playing perfect poker, maybe perfect chess, perfect Go. Those games that require a lot of computation in the future and have a very fixed states. And this kind of thing you can just use a computer and bash through because computers are great at that, great at number crunching. But if you want to apply this kind of number crunching to the real world, there's endless possibilities. It's just not possible to optimize everything. So perhaps one way that humans are general is that we don't optimize for everything. In fact, I don't even think we optimize at all. We are just basically choosing things that match our context. So in some sense, we are a pattern matcher. Oh, like you see this cup here, what's the most relevant context that comes to your mind? To me, it is drinking from the cup, right? So something like that, you know, you don't exactly need to optimize. So this brings to the point that, you know, some people can do certain things at certain situations that are totally uncalled for, but that's because, you know, they're just doing pattern matching. Like, you know, if you take another example, like if I were to like take up the cup again, some people, you know, because if they are used to playing with toy cups, you know, they will just throw it on the floor. You know, that's perfectly fine to them because they associate the cup with throwing, right? But, you know, sometimes that may lead to unintended consequences. But, you know, somehow or another, most of the things that we do when we associate, we don't lead to hazardous outcomes. That's why we can still survive. Yeah. So I think pattern matching is a core tenet of how we think, not optimization. So like reinforcement learning, I think focus too much on the optimization part. All right, one day I'll do another session on optimization and intelligence, so we can flesh out more. But back to general computer control. So this whole chain of cognitive processing is quite interesting because you can use this to solve arbitrary problems. Like a lot of things, you need to first get the stimuli in, which is the information gathering. You need to think about what's going on. You need to decide what to do next, that's task inference. Then you need to choose what you need to do next. So this whole thing can be characterized as a pipeline, all right? And what can this solve? Okay, if we do this correctly, we can solve stuff like we can navigate apps, okay, everyday software, professional software, that's apps also. We can also do other things like games. And in the future, if let's say we don't restrict to keyboard and mouse, because right now the output is keyboard and mouse. If we don't restrict to keyboard and mouse, if output is motor actions, we can even do it on robots. So this could lead to quite a general system because this pipeline that they are describing here is quite generic. And you can see underlying all of this is something that I like a lot. It's called memory. Okay, because memory is used to learn, all right? You don't want to have a system that doesn't adapt, right? Like if you don't have memory, you cannot learn from what you did in the past. Then your system would be doing the same thing again and again and again, regardless of what's the outcome. So with memory, at least okay, I pick up my phone right now, okay, and it fails. Let's say it fails, then I know, oh, maybe I grabbed wrongly. Let's change the grab. Okay, then I'll grab something else. Oh, yes, it succeeded. So if I don't have the memory of the past, I cannot do such a decision to correct my actions, to change the way I think, or change the way I act in order to achieve an outcome. So memory is very important, and memory also allows you to take what you have learned previously. Like if I can drink from a cup, I can learn this with a new cup. Yeah, because I can associate a new cup with the action drinking and I can drink again, So this memory is very important. In fact, I think 50% or more of AGI would be memory. I mean, the other 50% would be how to process images, because we are not done with that yet. so there's a lot of things that we have not solved with memory. In fact, this paper also did not solve the memory part. Okay, but at least the framework that they are thinking of, I think, is quite generic, and yeah, it managed to do a decent job at the game. Although I'm not too happy with the way they did certain hacks. Later I'll explain to you why. Okay, before I move on to the next slide, any questions on this general computer control? All good? Okay, so let's move on. So general computer control, as I mentioned earlier, is a setting whereby agent controls a computer using standard actions, okay, using screen, and they even have this optionally audio. It's not in the paper, but optionally audio is because games sometimes they use audio to tell you some clues. Right. So right now, they basically turn on speaker subtitle names so that they don't have to rely on audio. They can just rely on the text on the screen to decipher what's going on. Okay. So this also means that there are some actions like open cabinet, because there's no audio feedback, you don't know whether the cabinet is open until the character moves. Okay, so this is one of the limitations of the work right now. So I think audio is still important for games, especially for games that use that as a feedback signal for the player. All right. So what's the thing that we get as output? Output will be keyboard actions and mouse operations. So actually this is quite generic, because if you think about it, even if you map this to a robot, as long as the robot is running on some software, right? The keyboard and mouse operations, in fact, maybe you just need keyboard operations, like it can already tell the robot what to do. So if you think about this general computer control, actually is quite generic, because anything, as long as you have a software, you could potentially use this GCC to do it. So yeah, I think this is probably the way to go. OpenAI is also trying to do web agents, app agents. So they are also moving towards this general computer control. Everyone's trying to use large language models to do it. I don't think large language models alone will get us there. We still need a lot more investigation into memory and how to process images. So I will cover this in detail later as we go through how the authors did this for Red Dead Redemption 2. So as mentioned earlier, you see you have a screen input, image, text, audio input, goes through some processing model, which is the pipeline I described earlier, like the information gathering, the reflection, task inference, skill curation, and then action planner. And in the end, your action will come to the keyboard and mouse. Okay, so before we move to the paper proper, I just wanted to ask a question. So everyone's talking about AGI right now, artificial general intelligence. But the question that I have is that, are we truly generally intelligent? Like, are humans considered AGI? Like, okay, let's have a small discussion here, maybe about 1-2 minutes. Who here thinks humans are intelligent in all general ways? Raise your hand. Wait, no one raised hands. Who here thinks humans are not intelligent in all ways?
I think they're generally intelligent.
Okay, you want to explain why?
Yeah, you can do a broad range of tasks, and then you only, like, let's say you're a baby, and I mean you were a baby, you don't really need to learn or see too many or learn from like thousands of data sets to accomplish a task. You see it once, and then you can roughly get 90% done. So
Okay, so yes, in some sense, what you're saying is that babies observe the world. This is what Yan Lokun says also, observe the world. Then after like few short examples, can do the task. Okay, so this is more like building some form of model in the brain, and then like using that model to use as context to do to learn quickly from new tasks. It's something like when you do context prompting in LMs. So it's something like write this in Shakespeare. Yeah, then you just say like I am a student, something like that. Yeah, so you can use the LM to ground or you can give it some examples. Okay, this is the 0-shot example. You can also ground it some example. Example 1 is this. Example 2 is this. Do this. Yeah, so you can do something like that. So yes, we learn very fast. We are very adaptable, and that in large part is due to the way that we learn from the world without any sort of signal from the world. So it's like we just need to do next state prediction or next token prediction for LLMs, and we can learn a lot from there. We can learn the structure of the world. We can learn the interactions and so on. So I think this is yes, this is a good point to bring up. Like we learn pretty well from observations, but the main question is still not answered. The main question is like, can we learn all sorts of things? So I think that's the question I'm asking. Like, yeah. So any other anyone else have any other feedback or any other comments for this?
Yeah, if I can. I know Sprite has this light bulb up, but I guess what you're trying to get at is like generally intelligent, like as a turning problem. Like, can we generally learn and abstract the general idea of any possible problem in the universe? And does that get into like mathematics? Like, is mathematics like the baseline of the universe? So we consider that like the baseline for any other description, like how mathematical our brains are and like the algorithms of the neurons, I guess, is what you're trying to get at. Like, can we like, I guess there's like a lot of questions you could bring up when you say generally anything, because I think humans are very practical creatures. We kind of evolved that way. We got very generally good at tools. So in general, we can pick up on how to build a tool that helps us do something really well. So like I couldn't say I can computate Heisenberg principles and Heisenberg formulas off the top of my head like a computer could. I just can't. Like I'm not wired like that. I don't even think my neurons could even figure out how to do that well if I trained them really hard, like a Mentat from Doom or something. I don't know if I could do that. But I think like humans got really good at finding out how to generally build any kind of tool we need and then let that tool do the work for us. So like even in this, like we're trying to develop AGI and computer science and stuff, right? Like I don't know the answers and I can't computate how to do that just off the top of my head with pure math and build you a machine that does that. I can, however, build a machine that could somehow figure that out via algorithms and then experiment with it and build a general kind of tool that can help me with that. I couldn't do it just by myself with just my only brain. I would need a machine to help me like, run simulations and experiment and, find out what works and what doesn't. So I think those are like kind of my thoughts is like tool use.
That's a very good point, actually. Like, actually, if you think about it, like us humans. We can do a few actions like hands, grasping actions and walking, running, moving your body and dancing, that kind of stuff. But, we can't fly, we can't levitate in the air, we can't dig well underground. But we have conquered both the sky. Okay, I wouldn't say conquered the sky, but like at least we can go up there. And we can go down to the sea, down underground and so on. It's not actually because of our physical abilities, but yes, we are able to get tools to do stuff. And that is one big point. Okay, I think you brought up a huge point, is that we are only as capable like as our own baseline abilities, as well as the tools that are equipped with us to us. So to answer that question of whether we are generally intelligent, yes, we can do a lot of things, but to be fair, all of us are humans. We only think in a human kind of way. If you think about it, we cannot like stop an ultrasound. We cannot see infrared. We cannot disappear into the wall. Maybe there's a fourth dimension, someone can transport that. So we can't do a lot of things. So maybe the whole possibility of things that can be done in the world, like humans can do this amount. Then there's this amount here that we cannot do. Okay, but why haven't we decided that, oh, we cannot do so much? That's because we are interacting only with ourselves. So we have a fixed bias and we think that this is all that is important. So like for a while, okay, anyone can tell me, for a while in artificial intelligence, what has been the benchmark? Like people say that if we can win this game, we have achieved AGI or achieved superhuman intelligence. You all know the benchmark that people have been talking about? Anyone? Which like game is considered like the pinnacle of intelligence?
Go.
Go, yeah. Actually, before that, it was chess. All right, so chess was considered the pinnacle of intelligence. People were saying that, humans cannot do this well. You need a lot of brain power, you need a lot of thinking, to do this well. If computers can solve this, they will be superhuman. Okay, guess what? We have solved it. Okay, we have Deep Blue, Kasparov. Okay, but have we solved intelligence in general? No. Okay, we are still stuck at a point whereby, I'm very good at this game chess, but can it go outside of chess? No, it doesn't. AlphaGo, look at AlphaGo, Bits Go, AlphaZero also the same thing. Okay, it only does well at Go. You try to do it for something else, you need to relearn from scratch again. And that's just not how the human brain works. So maybe the way we work and the way these computers work are quite different, because we can do a lot of things, but can we be the master of any of them? Not really, like in order to be a Go expert or chess expert, you need to spend years of your life practicing and practicing, looking through the search tree, refining your moves and so on. That takes a lot of effort because our mechanisms in our brains are not built for that. Okay, we're not built to optimize kind of stuff like that. Yeah, so computers are great at that, so they can win us. So I mean, you think about it, would you consider a computer smart if it can do 10-digit multiplication faster than you? No, right? I mean,
No.
yeah. Yeah, Brian, you want to say something?
Oh, I said no.
Sorry? Yeah. So anyway, I was just saying that, the way the computers work is quite different, but we don't consider them intelligent. We don't consider a computer that can multiply 10-digit numbers intelligent. Okay, that's because, we treat them as like, oh, that's what they're meant to do. Like humans, the same thing, like we cannot do everything, but we treat ourselves as intelligent. Yeah, maybe this is a personal bias and so on. So I just want to bring about the point that, people talk about AGI and so on, but, actually, I think in the whole subset of possible actions, humans can do like less than 1% of it. So I just want to drive home this point that, AGI is a misnomer. Like we shouldn't actually be talking about AGI in some sense. We should be talking about artificial, generally human intelligence, because like we are just interested in what humans want. All right. So the thing is, can we create an AI that can do anything well? Okay, let me just put this point in bold here, right? Can we create an AI that can do anything well? Okay. So this is my answer, okay? No. All right. So, I mean, you're free to debate this point, but I always feel that intelligence must be grounded in some context. Like, in order to be intelligent, considered intelligent in some area or some competent in some area, you need all the necessary skills there. You need some form of grounding information. If you lack any of this, to learn a proper skill or to learn a proper action in the environment that you have no information about, it's impossible. It's not impossible, but it takes so long. It takes so long. Like, take for example, if I were to play with you a game where you need to guess yes or no for 10 questions in a row, I don't tell you the pattern at all. So it turns out that maybe I use a random number generator, and then the yes and no is totally random. Maybe the first is yes, second is no, then yes. You need 2 to the power of 10 tries in order to figure out like the entire sequence. So for this kind of stuff, if you have no grounding information, you will take forever to figure it out. Imagine if you need to do this for 1,000 times, right? You need to guess yes and no 1,000 times, and you need to do exactly the correct answer all the way to the end in order to be considered like problem solved. Can a general agent do that? Okay, I just want to ask you, can a general agent solve a chain of 1,000 yes/no questions to figure out the correct sequence? No, that's right. And that's what reinforcement learning is trying to do. They're trying to do this kind of very edge cases. It turns out that in the world, problems are not that difficult. You see, if you have a burger in front of you, just eat it. All right. And like for a baby, if they see a breast, they just suckle. So this kind of like stuff could be inbuilt already. And it's already grounded in the kind of context that that we are meant to live in. So I would say that the whole notion of AGI, I don't think we'll ever reach AGI. But we can reach a point whereby computers can be better than us at most tasks, in human-related tasks. That I believe we can do it. So why am I spending so much time on this slide? Because the authors want to build a general computer interface for any kind of interaction. I would say it's impossible, right? But we can limit the scope of it to some common applications. Yes, we can do that. Okay. Questions or clarifications before I move on? Okay, good. So this is again same point I want to make. Are games good enough for AGI? So it's like the authors want to use games to do AGI. I think games are great. Okay, games offer a virtual test bed. So if you know, like, if you have a robot, you know, it takes a lot of things to make it work. You know, Boston Dynamics, they tried to do robots. Now recently, humanoid robots spend millions on billions. I don't know how much the exact figure, but in order to get the robot to work, you know, they need to hire a lot of engineers, make the parts and so on. That takes a lot of money. But you can do the same thing if you just use a physics simulator, maybe on Unity or so on. You can actually simulate a robot moving. So yeah, games are great and cheap ways to simulate like actual interactions with the world, with the game world, of course. But of course, this may not be reflective of the real world. The image, the physics may not be there. Like in Super Mario, you can jump very high. That's not possible in the real world, you know that. So maybe you can create games. So the mitigation is create games that mimic the world. So there's one game, okay, I'm not sure if you all heard of it. It's like, you know, those F1 races. There's this game called Gran Turismo. You know, they simulate the F1 cars. I think it's F1 cars. Yeah, basically race cars. And, you know, it's supposed to be simulating the real world quite well. So the thing is, people were saying that, you know, if you can play well in Gran Turismo, you can actually be a great racer as well, because like it's about the same. Okay, so if you can do game environments like that, well done. Yeah, you save a lot of problems with the simulation. And, you know, if you were to use RL methods, you need is data intensive. So you could spend like years in game time and learn everything needed. So that's what most robots right now do. Like if you have those robots that, you know, you grab the cup and stuff, they do billions of simulations just to grab it well. And that's because RL is not good. So if you use a better method, you will learn it faster. All right. So games are needed for inefficient methods like that. Okay. If you actually have efficient methods of learning, you don't need games like that. You can just do it in the real world. All right. So that's games. All right. The second one is games can help with long horizon planning. Sure. Games like Go, you know, you need to look at the whole board. Yeah. Maybe even like Sonic, you know, you need to get some power up before you fight the boss. But having played Sonic myself, you know, even if you have no power ups, you can still win most bosses. So maybe it's not that long horizon for this kind of games. Minecraft is definitely a long horizon game because you need to craft like diamond pickaxe to go to certain areas. Nether portal, you need to go and fight certain bosses before you get the parts and so on. So that requires some long horizon planning. But the critic I have for game worlds like that is that, you know, in the real world, the boss is not going to wait there for you, you know. the exact things to do may not be the same sequence. Like if I want to get from here to the office or to school, you actually need to do certain things differently each day. because maybe your bus broke down, the train broke down, the taxi didn't come, you know, that kind of stuff. It rains, maybe I need to bring an umbrella. So that stuff in real world is not as fixed as a game, right? In the game world, it's much easier, right? But games have one good thing, is that if your game is doing some action, like some tasks, like in Minecraft, you're building a house and so you can actually get the game to feedback to you that, oh, the action is completed and so on. So you can have a score that you can use for reinforcement learning. But what I mentioned earlier is that if you optimize for one game alone, you know, it generally doesn't transfer to other games, non-related games. Yeah. So another thing is that, you know, what if games don't have an objective score? Okay, anyone want to guess? Okay, if a game doesn't give you a score, like for example, if you build a house, you get 1 point. If let's say the game doesn't tell you at all, you build the score at all, how can you know that you have built the house? Anyone want to guess? Like, so this is like Red Dead Redemption 2. There's no like score meter or anything. Anyone want to guess? Like how can we get like whether a task is completed without the game giving you that signal?
You have to give it like context and store it in memory, and you have to do like task learning to say that you completed a certain thing.
Yeah.
But you have to think it yourself.
Yeah, correct. So you had used some interpreter, like in this case, they use GPT-4 to just give the game context and ask it to evaluate. Okay, so this is also used in methods like say can, where they use the robot and they go and grab the Coke can and pass to the person. They also use the internal model to reflect and then see whether the task is completed. So that's okay if the large language model is already grounded in such tasks, like pick up a Coke can. That's normal. You've seen that in text. But if I ask the large language model to, you know, go and disappear in thin air, you know, or like fly up, it may not have the idea to like know how to evaluate. So this is a gripe that I have with methods that use large language models to evaluate task outcomes, is that if you don't already know what the task is in the knowledge bank of the large language model or in the pre-training set, you may not be able to use it to evaluate. Like I've tried before, like I've tried to ask large language model to evaluate a novel task that I'm quite sure is not seen in the training set. If you can describe it quite well to match the distribution of the training set, like mix and match certain pieces, then yes, maybe you can evaluate well. But you know, most of the times, if it's not seen that task before, it doesn't really know how to do it. So this may mean that, you know, maybe what we need to do is we need to give it certain outcomes that have objective scores. Like, I don't know for humans, like how we evaluate our tasks, but you know, a task like drinking water and eating, you can evaluate it whether your tummy is still hungry after that or whether your throat is still thirsty. So you have body sensors that can tell you like whether a task is completed. So that's what we are lacking for games right now. But that's not a problem, okay? Because if games are built by us, we can always build in this kind of objective scores. Okay, I'm just giving you an example of what happens when we try to do generically arbitrary games, like what the paper is trying to do. We will have these issues, and I don't think this is solvable. Yeah, I don't think this is solvable. We cannot just arbitrarily evaluate something, especially if it's not seen before by the large language model. It's not 100% here. Okay, so all that said and done, I think games are still a good platform for learning, especially to learn stuff that especially if the game is complex enough to mimic the real world, you can actually learn interactions there. And slowly and increasingly, you can see that we are moving from like more abstract to more concrete, right? You see Go is a bit more abstract. Then we move on to like Sonic, Super Mario. Some people did Flappy Bird. I think Flappy Bird is easy, but yeah, so there are some things that and move on to Minecraft, and now you see more and more attempts, like in this attempt, Red Dead Redemption 2. And soon we'll move on, maybe VR simulations and so on. I think we will only get better. So there's a lot of promise to use simulation to reach AGI. And eventually, once the simulation is complex enough, you can just transfer it to the robot. So that's a nice path, actually. Questions on this slide? Okay, so what are the challenges for this kind of generic control? First, we need to tackle image or video observations, which is very common in the real world. Like I think almost 70% or more of our brains are dealing with vision, because that's a very important sense for humans. So we use that a lot. You try shutting your eyes and walking around the room is very difficult, right? So that's one thing. We do text as well. Text is because we use language. Okay, for species that don't use language, text is meaningless, most probably. Audio is because we talk to one another. So all these kind of things we need to take into account. Okay, I mean, of course, there are other stuff, like touch, touch, sensory motor, but all this not for computers, because computers don't need to interface with that. But if you have other sensors, you can probably interface this as part of your observations. And so the system itself needs to know how to do all this, and this is not easy. Okay, we haven't solved image yet. Text, I think we are quite good, like 90% there maybe. Audio, getting there. Okay, so a lot of things is because these observations are very high dimensional. So this is what Yan LeCun would say, like text is easy, image is hard. So I completely agree. So that's also why like a large part of our brain, goes into processing images. The visual cortex is huge. Yeah. So the observations, if we can sort of interpret these observations, and I like to use this thing called multiple abstraction spaces. So we cannot just view like image as one image. We have to do it in different domains, like filter out the objects, filter out the text, maybe filter out the scene, filter out the actions, and so on. So if you just do only one abstraction space, which is like what most methods are doing, you will lose information. So you need to do it to different domains and so on. So this is something that we have not solved yet. This paper tried to do something like that. So I'm quite happy with the kind of approach that this paper did for images. I think it's along the right path. All right, the other thing that is difficult is that you need to control the output space well, because the output is high dimensional as well. Like the mouse, just moving the mouse, there's different ranges you can move, different speeds. You have different direction, ranges, and speeds. So this is difficult to actually control well. Keyboard is much easier, it's discrete, but keyboards have a combination of outputs as well. So this is not easy. And I think this, if you just use a traditional reinforcement learning approach, it will be very hard to learn, right? You need to abstract out. So again, in the out action space, needs to be abstracted as well, so that it can be used in atomic ways. Like you want to make sure that the mouse movement can be used, like move left, move right, can be used for different tasks as well. So you learn the move left, you can use it all the time. Like if you learn how to write the letter A, you can use this to form different words, and all these words you write A in the same way. So you have different ways to learn this action space, hierarchical grouping maybe, or like you already give it some fixed preset moves. So this paper does that. I think they also they tried to do this quite well as well. So this too, I think is not bad. So the other challenge we need to do is that we need to solve a partially observable or changing environment. So because we need to constantly remember and reflect on these interactions, we need memory. So let me highlight here. Memory to learn from the past. Yeah, can you imagine a system without memory? Imagine a system where it just says hello whenever you say hello. So I say hello, then you go hello, 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 hello. So it will never end, you see. So if the system has some memory, after I say hello for the third time, then maybe the system can tell me, you have said hello 2 times. Is there anything else you'd like to do? That kind of stuff. So it feels more realistic and like more like human being. So I think this is how you can tell human beings apart from toys. All right. You try saying hello to a human being like 10 times and see the reaction of that human. All right. You do this social experiment. Yeah, initially maybe the person will just say hello. Then after a while, the person like, why are you doing this? Right? You try it. Just say hello 10 times continuously to one person. Okay. If the person keeps replying you hello in a very joyful way, that's not a human. All right. that's at least how I think, like, we have this grounding in memory to interpret what's going on now. If you don't have this whole set of memory, which I think is very important, you won't be able to interpret the world. You won't be able to survive in this world because you won't know what's going on. Like if you see a snake eat up a mouse, right, and you store that in memory, then when the snake comes to you, you better run away, right? Because you know the snake is going to eat you up next, or at least based on inference. But if you have no memory at all, you're like, oh, what a cute snake, then maybe that's it. Then that's the end of your life, right? I think humans have an inbuilt fear of snakes. maybe because that happened back then. So so this is an interesting question. Can memory be transferred generation to generation? Okay, I think yes. Okay, but there's no scientific explanation yet for this. Yeah, so you not just learn from the past, actually you also pass down, maybe pass down through interactions with your younger ones, or just general societal know-how, you can preserve that memory. So also another thing is memory is not just in the individual, it is in the whole society. So there's group memory also. Like, okay, so I don't know how many of you here are married, or at least like have some significant other that you are talking to. But if you are having this kind of relationship, you realize that if the other party is better at certain things, like for example, my wife is better at cooking, she'll just do all the cooking, and then I don't do it. I'll do all the navigation, and she doesn't do it. So in this societal things, at least in a group setting, the person who is normally better would actually do it, and soon you will forget, or you'll lose the memory of how to do it. Like for example, I don't really cook much, so I don't really know how to use. I mean, I still know how to cook, but of course my knowledge of that will decrease over time. And similarly, my knowledge of navigation will increase over time, or at least maintain, because I keep doing it. So this shifting of memory is like because of limited capacity of memory, but also because as a group setting, all of us as a group will fulfill a united task, and we just need to do like what each person has been assigned with, and the memory is used to make you perform better. So given your limited capacity, you slowly shift to what you do more. I mean, you think about it right now, all of you are here for this kind of AI sessions, like what you don't do, soon you will forget how to do it. Yeah, so this is just the memory part for multiple agents. Of course, in this setting for the Red Dead Redemption, there's only one agent. Okay, so this group setting here is not really covered, but I really think that if you want to solve arbitrary stuff, okay, if you want, not really, if you want to solve complex stuff, you need a population. Okay? A single individual, just by exploring and exploiting, you can only get so far. So that's actually the last point. But let me just finish up this point here. You need to constantly replan based on the training environment. That requires memory as well. And also you need to have knowledge of what action you did in the past and whether it's successful or not. So this last part here, I think this is the difficult part. You need to self-improve. You need to explore. Okay, because if you just keep doing the same action again, it's like, I don't know if you heard of this thing called the multi-arm bandits. Who here has heard of multi-arm bandits? Multi-arm bandits is basically you have like X slot machines. How do you know which is better? Who here has heard of multi-arm bandits? Okay, so in a multi-arm bandit problem, let's say you're at a casino, you want to pull that machine, you don't know beforehand what the machine is, whether it's good or bad, assuming that each machine has a different distribution. You need to try out each machine, right, before you conclude. So if your tendency is just to stick to one machine, you will never find out the rest of the outcomes. So similarly, I have decided to focus on AI in my life, and I will never know what it's like maybe to be a painter, to be a musician, and so on, if let's say I don't go down that route. So like, how do we do this kind of exploration when we only have so limited time, right? Like, if I could do everything, yes, I will explore everything and find out what's best for me. But the thing is, I don't. So this needs to be done, I believe, at the population level, where different people have different interests, different backgrounds, and they do different things and they share knowledge. So exploration can be done at the population level. So Red Dead Redemption 2 here, the exploration is not good. Okay, there's only one agent here. I think for most single player video games, it's like that. Like if you just play alone, like Minecraft maybe, you can only get so far. Yeah, I'm not a Minecraft player, but I'm very sure that most people who play Minecraft will look at some guide as to how to craft items and so on. These guides are created by people, maybe by the game creators and so on. Just a single person cannot just explore such a vast space. You need a group. In fact, even a group may not explore sufficiently. No, we are all trying to solve AGI here. Have we solved it? We may never solve it. Okay, because we may never reach the search space that is needed in order to solve it. Okay, but the thing is, if you just do it with an individual agent, you will never achieve it. I mean, if let's say a population of billion or zillion agents cannot do it, what makes you think a single agent can? So I would like to always quote this example, is that take a look at the computer right now. Like, will the computer have been invented if it's just one single person doing it? That person needs to know microelectronics, needs to know software, needs to know hardware, needs to know the structural components, needs to know how to do electricity, how to do AC, AC is the AC/DC, as in the kind of electricity supply. So one single person needs to do all this LED display, maybe, it's so hard for one single agent to do it. But collectively, as a group, you can do it. So I think this part here is one of the key things that is not solved yet, because we just don't have the ability to scale up to billions or millions of agents. Maybe because GPT-4 is still quite expensive. But once we can do that, okay, we can do a lot more things. So I think this challenge for GCT is a real one. And once we solve a lot of these things, we can actually slowly get towards AGI, or at least artificial human general intelligence. Okay, it's based on what humans think are good. Okay, I would like to say that a truly general system doesn't exist, because it's just you just can't do things that you're not equipped to do. Yeah, that's simply put. Okay, yeah, I went a lot into this slide because I think their vision for GCC is a good one. I just don't think that it can be truly general. But I do agree with how they're trying to scope the problem here. And any questions on this? Okay, let's move on proper. So let's talk about a previous system that does something similar. So the previous system is called Voyager. So Voyager was something that was used in Minecraft. Quite an interesting mechanism, I would say. One of the first of its kind to do an agent that can keep improving by itself. So the first thing that the agent does is something like the teacher. So there will be a list of tasks that the teacher would know. Okay, so this one, how it knows, of course, it needs to, have some grounded knowledge. So again, it's not general. They really put... So Voyager has a lot of hand-engineered prompts, okay, in order to make the whole system work. In this paper of the Red Dead Redemption 2, they said that they want to make it generic and not use handcrafted prompts. That's not true. All right, I looked at their code, everything is handcrafted. Okay, so if you ask me, Voyager and this Red Dead Redemption 2 agent, both only solve that game itself. It won't generalize. Okay, so I think this is something quite telling, is that maybe intelligence isn't so general after all. Okay, so anyway, let's go back to Voyager. You look here, we have this mine, woodlog, make crafting cable, and so on. So the teacher would choose a task that it thinks the student can actually do it properly. Okay, so this is something called doing easy tasks to hard tasks. Okay, so you can transfer some of the earlier learnings to the later tasks. Okay, so this is otherwise known as curriculum learning. I mean, it's called curriculum learning because that's like how curriculums are structured. It goes through the basics first before the more advanced. So this is a good way to learn, because if I ask you to solve a differential equation without teaching you how to do addition, you will definitely not be able to do it. So that is the key concept of learning. Like, we should learn from simple tasks and go to harder tasks. So that's the automatic curriculum. In the Red Dead Redemption 2 part, there's no such curriculum, because the curriculum is the game. Later I'll tell you why. All right. So this next part, the student will learn through interaction with the environment. They will try to code out something given some ground truth skills. Like, maybe I already give you some basic recipes, or over here they actually have a database that they can search, Minecraft database with all crafting recipes. Yeah, so there's some external knowledge here. Again, intelligence is not general. You need to ground it somewhere. So you have all these recipes. You try to, create a program that can, in fact, you already know how to do certain API actions, equip. This is not an action that you need to learn. It's already inbuilt by the MindFlayer API. Okay. in the Red Dead Redemption 2 paper, they also inbuilt with quite a number of APIs, I would say. In fact, so many APIs, I actually doubt whether the agent is learning anything. But yeah, so let's take a look here. So we have the code over here that it's that uses this, and the code here would be executed in the Minecraft environment. Eventually, the environment will feedback whether there's any errors. If there's any errors, compile error or so on, or like the action didn't achieve the task, the environment itself has been programmed to give some constructive feedback, like saying that, oh, unable to find target, unable to craft the recipe because missing what. So the environment gives some feedback, and this feedback will be used by this code agent again to, you know, generate more code, and you repeat the cycle until like hopefully the task is done. Okay, there's also another part that like self-verification, where they use GPT-4 to give feedback or critique. I think this part is good. Okay, this part is also similar to what the Red Dead Redemption 2 agent did, or CRADLE did. So they also use the eternal self-reflection to give some critique of like, oh sorry, they have a task completion checker. So that completion checker will also give a critique of like how to solve the task if it's not done. All right, so this part here of giving critique, there's this paper called reflection. So basically they find out that giving reflections helps solve tasks, like it improves the performance by 50% or more. Okay, I can't remember the exact number, but just reflecting on the output of the large language model itself could already improve the large language model. So this part here is useful, but again, I'd like to, you know, tickle your brain a bit. Can it work for any kind of problem? Can the feedback work? Okay, what if GPT-4 doesn't know how to do it? So the answer is this feedback won't work for all cases. Okay, I tried it. I use it on the ARC challenge, the abstraction reasoning corpus. I gave reflection feedback. If the agent doesn't know how to do it, there's no way you can give good feedback. Like if you're not a law student and I ask you to reflect on whether the law passage is correct, you wouldn't give good feedback at all. Yeah, you wouldn't know. So this part of the feedback loop, if it's done internally, it may not cover all cases. Okay, but whether can it improve? Yeah, for arbitrary, for simple cases, yes. For more specific cases, a better way to give feedback. Okay, this is not done in Voyager, but this is what I'm saying. Is via tools. So if let's say your tools are meant to do certain things, like you have a calculator to calculate numbers, the calculator can give you an error. Hey, your 3-digit by 3-digit multiplication is wrong. You should get this answer instead. These are the steps needed. Maybe if your tool is that good, you can learn from the output of that tool and slowly, you know, you'll build your memory bank and you're like, oh yeah, 3-digit by 3-digit multiplication. Yeah, I should have done it this way instead. Yeah, but if you have no external signal to guide you, you are as good as yourself. Yeah, I mean, you can reflect a bit on your actions, but you won't improve much. Like I play Go, you know, like Go is the black and white stones game. I play Go. I'm about 5Q, now going to 4Q. And how I improve is, yes, one way is to play with other people online, but I improve a lot more by asking people to tell me. Like I ask a tree dan to tell me, like, hey, what did I do wrong? Then the tree dan will point out some of the moves that I did wrongly. And basically, I learned from the explanations and so on. More recently, I learned from a software called Katago that will just tell me where the wrong moves are. Yeah, so that feedback is important. If not, you won't learn at all. So a lot of these agents right now, Voyager, in fact, this Red Dead Redemption 2 CRADLE doesn't have this part because it's just relying on GPT-4 to give you the answer, to at least check whether the task is completed. Use GPT-4 to give you a constructive criticism of how to do the task. That won't work. Okay, that simply won't work. Okay, you can see later in the results, it doesn't give you enough to like learn something new. What you see in this Voyager and what you see in CRADLE is just a reflection of what GPT-4 is capable of. Okay, anything beyond that scope of GPT-4, these agents will fail. And this means that we don't have the right tools equipped to solve this task yet. You need to learn these tools, or you need to have these tools to give you the feedback so that you can learn how to interact better with the environment. All right. So Kyren, you asked, so for unknowns, we have to rely on outside tools. Yes, I would say so. So if you don't have external feedback signals that are grounded to the environment itself, you won't learn. So like for games, okay, you treat for example games. Let's say you are playing a game like Flappy Bird. Flappy Bird is the bird that flies up. Like if the environment doesn't tell you like, oh, you hit this pillar, that's why you died. I mean that's how you see it visually. So you can adjust, your angle accordingly the next time. So the game will give you some feedback of whether it's correct or not. Let's suppose I let you play Flappy Bird now, but even you hit the pipe, you can still continue. But at the end of the game, I will just tell you your score. So you won't know where the error came from. You see, you're like, hey, how come I got a lower score? How come I got a higher score? Like, in fact, people have done this experiment before. Like they do a learning task, and then the task outcome doesn't correlate with what the person did. Like they just throw a random dice and they tell you like, oh, your score is 5, your score is 10, like that kind of task. You can't learn because you don't know where you did wrongly, you see. Yeah, so if you don't have a way to give proper feedback, you don't have that learning signal to ground your future actions. All right, Shang Ong, you asked which tools are useful for reflection and which part of reflection is useful for RLHF. So I think tools in general is just like based on the context. So if you are playing Go, you need a tool that can do the Go better than you to give you the feedback. Numbers, if you need help with numbers, maybe your calculator should be better than you at that, then it can give you the right feedback. All right. So that is how we use tools. In fact, for humans, we actually use each other to help us. Like if I don't know something, I ask an expert. The expert will give me the feedback. So that's why I say multi-agent is very important. All right. Which part of the reflection is useful for RLHF? Well, RLHF depends on human inputs, right? As the ground truth signal. So, if you want to do RLHF, you don't need the reflection because like you already have the ground truth, which is the human itself, to give you the answer. So in RLHF, I will argue the only important part is HF. The RL is actually not good. I'm not an RL fan. So if you just do HF, you can see a lot of current methods now like direct preference optimization. They don't even need the reinforcement learning part. So yeah, that is the kind of thing that, because we are trying to align to what makes a human think is good. So you just need the human ground truth, right? Yeah. All right, so let's move on. So this was Voyager. So one good thing about Voyager is that they have this skill tree or skill library, which can use the past programs. Like for example, you have this craft stone sword. This is actually from here. So you actually reuse your skills, and in reusing your skills, you can build compositionally small skills to build bigger skills. And this is a huge thing because if you can do skills like that, you can create more complicated skills and you can like navigate a more complex environment. But I would like to argue for Voyager is that this is like, because the Minecraft environment is quite hierarchical. You need to go through like wooden sword, then stone sword, then diamond sword. Yeah, so this works, but is it useful in general? May not be, like a lot of the skills we learn as humans, like we only do it once and then we use it as composition to another thing. Not really. So I mean there are some limitations to this, but this was the first attempt at doing some form of open-ended embodied agent. So how did CRADLE improve on this? So one thing for Voyager is that everything is text-based. So like the inputs from the environment, they will process it through some API to give the agent in text, like, oh, there are certain bricks in front of you. This is a wooden brick, this is a stone brick, this is a pig over here, that kind of stuff. So they actually use this thing called voxels, which is like some ray tracing kind of thing to tell you where it is and convert everything into text. Okay, Jarvis 1 improved on this by using image directly, like GPT-4 again, GPT-4v to process the image directly. CRADLE does a similar thing, but CRADLE does it even better than Jarvis. So I'm going to harp a lot on the image processing part for CRADLE because I think this is the key highlight of the paper, right? So they not just did image, right? I'm very happy with that. They also extracted out for each sub image, like the OCR for the image, and they also have bounding boxes for targets. So they did this thing called multiple abstraction spaces, which I agree a lot. Okay, you cannot just do everything in like, oh, this is an image, describe this image. You know, you will lose out a lot of things. Like, what about the specific detail at the top left corner? What about that detail at the top right? If I ask you to describe the image, generally, you will lose out specifics. If I ask you to describe in specifics, you will lose out the big picture. So I believe a truly general or truly intelligent agent would need to process things at multiple abstraction spaces, hierarchical and parallel. So you need to have, especially for a very complex domain like image, you need to have abstraction spaces that are of different forms. If not, you just use one, you won't get all the information you need. The second important breakthrough, okay, I wouldn't say it's a breakthrough because a lot of other papers have done it. Like they do memory, reflection, they summarize the memory, they do the whole sequence of past actions in text as memory. In fact, the memory also contains the image, but the image is in text form, like it's the process form. So this idea of multiple abstraction spaces in memory helps with decision making in the future. And then you have multiple ways of getting information. So if I were to say something, is that I believe memory is very important for agentic learning, and you cannot just store memory in one way. So you need to store memories in different levels of abstraction again that will be activated when different levels of problems come up. Like for example, if I ask you, like for example in this text, what is this text talking about? So the whole text is talking about CRADLE. So maybe I store that information as a summary. But if I would ask you, what are the different multiple abstraction spaces in CRADLE? Then, you know, image, OCR, this will be the specifics that need to be stored somewhere again in memory. And you can store them in different levels of abstractions, and you extract from the right level based on the question or based on the task at hand. And this memory, the different ways of passing through the different levels of abstraction is, I would say, as important as the different levels of abstraction in the images. Okay, because your image will directly map to, so okay, let me just draw out for you a diagram. So we have your sensory stimuli. Okay, and then we will have multiple abstractions. And then even more abstractions. Okay, so let me just draw the flow chart, right? So you have your stimuli here. It will go inside multiple abstractions. And each of these abstractions itself, based on like how you have done stuff in the past, your context, you can actually do some reflection or summary. So you can reflect, summarize. Okay, this helps you to plan more longer term, because when you reflect, you can consolidate a whole sequence of actions into like, oh, don't go to path A because there's a snake. You know, rather than saying image frame 1, I'm at the start of the path. Image frame 2, I walk a bit further up. Image frame 3, I move to the left of the path. Image frame 4, I see a snake. You know, that whole image stream of video is high dimensional. Maybe all you need to do is don't go to path A because it's a snake. So as long as you summarize it, you can use that for decision making next time. So there's a way to pass, to reflect, and so on. Maybe, and all this over here should be stored in the memory. So like this part here. And this memory will be differentially activated each time you need to do something. So this part here will go to your decision. So this paper is an early attempt to do some of this. They didn't do it perfectly, of course, because the agent did not learn that well. And also, like, in order to solve arbitrary tasks, they did not filter the abstractions. They put all the abstractions in the same prompt, causing GPT to have issues to focus on the right thing. So I think to improve on their paper, we need to kind of like make the prompts more targeted, you know, like maybe one agent does with this abstraction, another agent does with another one. Yeah, so stuff like that. Questions before I move on? All right, so this is how CRADLE does it. So first we have the information gathering step. We gather some information about the picture, okay, like the horse and the mini map and so on. And like GPT-4 will give some examples of, oh, there's this. Okay, so this things here would be processed further, okay, by GPT to say that, oh, what are the kind of stuff inside this patch, like show info, lead patch, shire, and so on. Like, you see, even needs to know that this is a left mouse button. It's not easy, right? So this if you look at my previous video called V-star, okay, you realize that actually GPT-4 is not good at positional information and also not good at identifying specifics. And you know what they did for V-star is that they just crop the image and then put to GPT to process again, it gets better results. So something like that also done for Cradle. They actually identified where the UI elements are using GPT. Okay, that's a questionable choice, okay, because GPT-4V may not get all the UI elements out. I think if you try look at app agent, they augment UI positions via XML for phone apps. Yeah, so if you look at it, all the past projects that people have done with GPT-4V has hinted, and I've experimented myself with GPT-4V as well. But GPT-4V is the leading image processing, though I think back end they use vision transformers which don't preserve this positional information. So it's lacking all these things. So if you want to do like interpretation of your entire image like that, you will lose out stuff. And you know, GPT-4V is not sufficient. This paper augmented with a lot more things. So I think that's a great job by the authors actually. So just wanted to highlight, you need to abstract out different things, and all this will go into different abstraction spaces. Like this is minimap. Minimap will also go into abstraction space for minimap to interpret what the minimap is. All right, then what we'll do is after this sensory stimuli has been processed into various forms, we do some form of reflection. We say that, okay, so I have some memory here. See over here, this episodic memory of the past. Over here is like the past 5 frames of what happened. Okay, so we can see that we have taken the action check Shire. And you know, we basically say that the action took effect since the secondary menu of further actions appeared. Okay, so I want to highlight this thing here, okay? The whole Cradle is too dependent on game observations, like on game hints. So a lot of how they view the task completed is whether or not the secondary menu appeared or whether the next part of the prompt here appeared. So yes, I mean, you could say that it's because in Red Dead Redemption 2, maybe the task that they give you at the bottom will tell you whether or not you finished the first task. Okay, but the thing is, the way that this whole system does it is very reliant on these UI elements here, and that I don't think is generic at all, because if you take away all these UI hints, if I ask you to lead the horse, right, and I don't tell you that the action has been completed at all, GPT-4 will keep doing it because internally it doesn't know whether it has done the action finish or not. Yeah, so this part here I think is a problem of this method. Okay, but it could be solved maybe with better image processing tools that can tell you, oh, I finished the action Shire the horse, even without relying on the game UI. Okay, because this game UI is not realistic. Okay, who here thinks that when you finish a task in real life, a pop-up menu will say that task completed? Anyone? Raise your hand. If I finish drinking water from the cup, will they tell me achievement unlocked, water drunk from cup? In real life, will that happen? No, right? Yeah, so this is a bit artificial. So again, this self-reflection after we get the images will decide what we do next. So over here, we already know that we have shired the horse. Okay, so now we need to lead the horse. Okay, so that's the next thing. And guess what? The game tells you what to do. so the game itself is actually quite helpful in terms of the tutorial levels that they tested this on. What you need to do, at least the task they need to do, is actually on the screen itself. So what they just need to do is to just extract out that task. So again, task inference will base on what task has been completed to see what next task should I do next. Okay, so after I've decided what task to do next, I will then do skill curation. So I have a list of skills that are relevant. So this is based on cosine similarity of the task compared to the function, the skill name plus description. So if you think about it, actually it's the same as how I did for task gen also. So this is how we select relevant functions in order to use it. So with this list of curated functions, we then form a list of next actions to do it out. Okay, we pause here for a moment anyone can tell me why it is important to do skill curation? Why not just put all the skills into the context of the LLM? Anyone want to answer this question? Why is it important to do skill curation? Okay, Derek, yeah.
It's like you brought up earlier with context. So when you overload the LLM all at once with the prompting, it just gives nonsense. Like it's way overloaded with answers and possibilities. You have to constrain its possible tool use so that it can choose optimally.
That's right. So based also on my experiments in the UP data, like abstraction and reasoning corpus, I find that if I put in too many functions, like for example, rotate grid, change pixel color, if I put in like 10 functions versus I put in 3 targeted functions, the 3 targeted functions will get the job done much better, because LMs, they tend to like interact based, give you output based on context. And if your context is irrelevant, right, it might actually give those irrelevant stuff as output to you. So that's a quirk of LLMs, and also a quirk of humans also. You see, let's say if I have, I ask you to drink water from a cup, and in front of you, I put like not just 1 cup, I put 10 cups, and maybe only one of them contain water. Okay, the chance of you picking up the wrong cup is higher, right? I mean, especially if you are not paying attention, you might drink something else. You might drink someone else's cup. Versus if I only give you 1 cup and I tell you to drink water, you see that it's more targeted. It's like, it's the cup. I can just drink like that. And that is essentially like what the skill curation is doing. You don't need all the skills. You just need the skills that can solve the task. But then again, this also is a point of failure, because if you miss the skill, you can't do the task. Okay, so this is a trade-off here, but I think the trade-off is worth it, because if we don't do the curation, there's just too many things that can be done. Like take for example humans, like we know a lot of skills. Right now, like I'm talking to you right now, the skill I'm using is to talk. Imagine in my brain, I need to process all the thousands of skills I need to do at each moment. I think that will be too much to process. So based on how relevant the context is, certain pathways get triggered in my brain, and this leads me to choose the actions that are related to it. So I like this a lot, because I believe the brain is context dependent. It's all based on your input stimuli to choose your next actions, to choose even what memories you trigger, right? So memory triggering is also context dependent. So over here, unfortunately, they didn't do this in their memory. Their memory is just take all the memory. Okay, I mean, I might be wrong, but in the paper, they didn't mention they use like cosine similarity or some ways to choose the memory. It looks like all the memory of the last 5 frames go in. So I also think memory should be context dependent. So yeah, this basically means that based on what you see at hand, like what's your input stimuli, you will trigger the relevant memory. Like if I see the cup here right now, I'll trigger the memory of drinking from the cup. So I mean, you can take this little experiment. Let's suppose you have a very, very famous or very, very impactful location in your mind that is associated with some music. Let's say, for example, you go to this theater and watch Les Mis. When you walk by that theater, will the song automatically play in your head? Like, chances are yes. I mean, because you associate like this location with this audio and so on. So, like it or not, even if you don't want to think about it, if you pass by a stimuli that is strong enough, the memory will be triggered in your brain automatically. Okay, so that's how you sometimes can feel sad just by looking at the picture. That you don't even need to tell yourself to feel sad. You just feel sad because in your brain, this inference process is happening automatically, right? And you extract the right memories to do the task. And I think that's how humans are so great at doing tasks. We can always, by pattern matching, find the relevant memories related to that current stimuli and use it for decision making. Okay, CRADLE did not use this, but I think that needs to be done. Okay, at least they did the skill curation part, and they also have some form of summarizing the memory. So like this reflection will go into memory. There's also a summarization pathway that will also go into memory after the input stimuli here. So I think they have like maybe the whole system, they have gotten 20 to 30% of the pathway, right? So I'm quite happy with it, because at least this is one of the first few papers I see that do multiple abstraction spaces in images. I'm very, very happy with how they did it. So later I'm going to spend about 10 minutes talking about image. which also means that I probably can't finish the whole presentation today, but I think this is very important. We will talk about how they did images later after this slide. Okay, so over here, like after you choose the list of actions, you just choose the next one, like lead horse duration equals to 2, and you execute out in the environment. Environment will give you some feedback, and then you go through the whole cycle again, like that. Yeah. Okay, so oh yeah, there's one other thing that I need to highlight here. This is the generated actions. So other than the list of skills you already have inbuilt, you also have this generation of actions. And how are these actions generated? This comes from the game prompts. Look at this, lead the horse. All right, and they even tell you lead the horse is what? Press E to lead. And this automatically gets translated into an action called press E. All right, there's also a show info over here. And where did this info come from? Ta-da! It comes from here. So guess what? Cradle is a very good interpreter of the UI in the game, and they map it to key presses. And this is reflected in the generated skills here. So at least they have gotten some parts right. Like if the game gives you advice, you better make use of it. So again, it's because of quirks like this that made me think that, maybe Cradle doesn't really learn. I mean, it's just based on the hints that the game is giving and just acting on it. And also using what GPT-4V knows beforehand about like horses, about actions and so on, and just using it for the context. And it also helps that the game world is very realistic. So this very realistic game world is a reason why people like this game. Okay. And this very realistic game world really helps GPT-4V. I mean, we have seen some studies in the past where we use image processing tools to try to process Atari games. And honestly, they can't do it because the Atari game world is so different from the real world. It confuses the image processing tool. So maybe this is actually makes it easier for Cradle because the game world is so realistic. It matches the training distribution of GPT-4V. Okay, so there's a lot of things that that make it easy here. And I think this realistic game world is not a problem because in the real world, this is also going to be realistic. So I think this is okay. Okay. And the only thing I can see that could be a problem if the game world doesn't give you the hints like what to do here. Okay, maybe it has a tutorial of how to do it. Then maybe all this in the retrieve already. So that's not a problem. But for the specific case of Red Dead Redemption 2, a lot of this is actually done on the game UI menu itself. So you need to learn while the game shows you. So, and maybe because this is a tutorial stage as well. So I think while it's dependent on the UI, it's also because the game itself needs to teach you certain actions. So maybe that's still acceptable. Okay, in the real world, maybe we already learn all these actions and we are just choosing which action to execute. So, I mean, the fact they can learn from what the game tells them into skills, I think this is remarkable. So this is remarkable that you can learn from game UI to skills. So this is again a step up above Voyager because they can learn instantly from this UI. Yeah, I see something in the chat. Okay, let's see. Who's asking? Kyren, you asked, how would this method lead the horse generalized to real-time simulation, not games? Probably poor, right? I think this, I mean, it depends on how realistic your leading the horse in the game is. If it's very realistic, it will generalize naturally to the real world, right? So I would say that the main thing is that if we can design a simulation that is very realistic, then if it can learn, if this kind of AI systems can learn in the simulation, I wouldn't be afraid to say that it will learn in the real world as well. Yeah. So I would say that there's not much limitation here. The only limitation is maybe our technology to simulate the real world. It may very well be I can simulate my daily life with Sims 100, if the game called The Sims. Like if they make it so realistic that I can even imagine myself to be in there, then if the AI can learn skills there, I'm quite sure it can learn in real life as well. So the main thing is, can it learn in the game world? The game world is just a proxy for the real world. So if it can learn in the game world, it will probably also be able to learn in the real world, as long as you make the game world realistic enough. So my only gripe here is that like all this here is like not very realistic, but this is a game after all. If we map this to like this E over here will lead to walking in the real world, then naturally it can lead to robots as well. So if your keyboard presses can lead to actual robot actions, then I would say yes, this can learn generic robot actions, provided the game teaches you how. So in real world, does anyone teach you, oh, press X to crawl, press A to cry? No one does that, right? I mean, how do we learn all this? And this is my hypothesis. Most of it is inbuilt. Okay, so like crying is not learned. You just cry naturally. Like breathe. Do I need to teach you how to breathe? Not really, right? You learn. Do I need to teach you how to eat? Maybe a bit because you might choke, but that is also quite inbuilt because it's based on the specific features we have. Like I learned how to grab stuff because I have fingers. If I have no fingers, there's no need to learn how to grab, right? Because like and how we learn how to do things is really dependent on our environment and our own physical limitations. So I would say that all this learning process could be like imparted from the generation above, imparted from society, imparted from YouTube videos. Hey, do you know someone learned how to drive just by using a YouTube video? so you can actually do stuff like that. So I would say that learning skills can come as like imitation, or it can come as guidance like this. It's just that in this game, because of the very nature of Red Dead Redemption 2 tutorial mode, or at least the first 2 missions are quite tutorial, most of the instructions of what to do come from the game. So while I say this is a limitation right now, this might actually be okay. Because if we have another means to learn the skill somewhere else, like as pre-built knowledge, or like someone guides us and we can learn from that guidance, then this is fine. Yeah. The only gripe that I have, and maybe I'll talk about this next week, is that some of the skills you can't learn them. Like, for example, there are some skills like shoot that is not learned. So if the AI were to learn how to shoot like a target, I don't think this LM method can work. Okay, because they have to inbuild it with the right atomic skills. If not just by pure random exploration to just shoot the target, the whole screen is so big. The target is like that only. In order for the random exploration to even go here, you need someone to tell you, aim your cursor there. Okay, maybe the game didn't teach you how to do that. That's why they have to do that as a pre-built skill. So that is one of the limitations. I think that if they don't have all these pre-built skills, they can't play the game. Yeah, they even have a skill to fight. So because like another limitation is that this takes 20 times the speed of humans to think. So if you were to not real time the fighting sequence, maybe by the time GPT-4V comes back with the response, your character is dead. So maybe they had to put that as GPT-4V limitation. Okay, let's see the chat. Okay, yeah, nothing. All right, so this is the key thing of the decision-making loop. It is a complex game, and the fact that they can even learn from the screen UI, I think that deserves an applause already. That's not easy, right? From this menu here, show info Q, it leads to press key Q. I think that's not easy. They basically managed to do mapping of the real world, mapping of the world UI to skills. And I think that is an achievement by itself, because over here to translate this even to something meaningful and to put that as code for reusable bits, I do think that that's a step above Voyager already. Because Voyager, the skills are actually mainly based on some database that they use for recipe tables, and they put that into the MindFlayer API. But here, from the image, you can get the skills. That's easily like an advancement. So you all heard of this 2 minutes papers? There's this guy who like to say, 2 papers down the road, things will be better. Yeah. So this is exactly what happens. Yeah, 2 or 3 papers down the road, you see, we have advanced. Yeah, so CRADLE is definitely an advancement. It's just that in the whole overall system I have in mind, this is probably just 20%. Okay, we haven't solved a lot of things yet. So this will be my last slide for today, because there's a lot more. Maybe I'll cover that next week. I want to hop on this point of vision and multiple abstraction spaces, because I think this is a very important part of agentic systems that use vision. And we haven't solved vision yet. So far, we have done stuff like, if you are familiar with vision stuff, we have stuff like ImageNet, that does classification of 1,000 target classes. There's also JPT 300. I can't remember JPT or JFT, but like this is the Google data set that is much bigger. And then they basically say that because they pre-train this vision transformer on this data set, they can zero shot ImageNet 99%, or 90+%. Yeah, so So far in images, in the image world, it's still largely supervised learning. So if I were to harp on this idea of supervised learning, is that you need a lot of human labels. And like if you do ImageNet classification of 1,000 classes, if something's outside of those 1,000 classes, you will know what it is. So there's a limitation with supervised learning, is that you don't know stuff outside of your labels. And also it's very time consuming to get labels. So for text domain, like for transformers, we know how to do next token prediction. We can learn from structure of any data, like any text data, you can predict the next token or next word, and you can learn some structure, some information. We don't have that for images yet. Okay, and that's because to predict the next image is high dimensional. It's very difficult. I did a video on IJAPA, image JAPA by Meta. They tried to predict the next, they tried to make an image into like patches and predict patches of the image. Okay, I think that's not a good idea, because like like if you block off like this part of the image, like try to predict it, sometimes you also cannot predict properly, even for humans. There's also a more latest advancement, I haven't covered this, but VJAPA that does this for video frames. But more interestingly, there's Sora by OpenAI that tries to treat the video sequence as a list of 3D patches, like patches per image and patches across time. I think that's promising. But all these methods basically haven't really solved the problem of, I mean, maybe Sora might solve it, like of doing self-supervised learning, where like take any stream of video and predict next image. Yeah, so if you can do something like that, self-supervised learning method, like how you do for tokens, you can learn a lot from vision. I think Sora is a very good first step towards that. So maybe I'll cover Sora, because I quite like the architecture. Yeah, just that they only use one abstraction space. They haven't used the multiple abstraction space yet. If they use multiple abstraction spaces to predict the next frame in the future, maybe they will have that much better. And they might even solve the physics problems that they are experiencing there. So image, we haven't solved it. We are still, I mean, I have a lot of ideas there, but I don't have the budget to run it. So, so I can only think of it. So hopefully when this larger corporations actually do some form of multiple abstraction space self-supervised learning, we would have achieved a big leap towards image understanding. All right, so this ImageNet stuff is great. I quite like Fei Li for trying to create this kind of data set, but it's not sufficient for the real world. Right? I don't think we can do this. We have to do some form of self-supervised learning. And I've been thinking a lot for this. We need to do this by predicting the next frame, but not predicting the entire next frame of the video, but predicting different domains. Like, for example, if the action lead the horse, like maybe the next frame is like, I'm closer to the horse, I'm this distance to the horse, this distance. You can predict by distance, or you can predict by, you know, saying that, oh, now it's a sunny day, you know, the next frame, it will still be sunny, you know, that kind of, so you can have different ways of predicting an image, and then these different subsets can group together to give you the full picture. So, right, more on how we train this next time when I talk about Sora and everything. But first, how did they get a very complex video game input into something that can be processed by GPT-4V? Okay, because they use GPT-4V here. So first up, we identify the keyframes from the video using VideoSubFinder. Okay, this is because, you know, a lot of instructions in the game appear as text. So a VideoSubFinder is basically a professional tool to, you know, if you are very lazy to watch a video, you can extract out all the subtitles for you and you get the subtitles. So that works quite well for stuff like, you know, this kind, lead the horse, or, you know, if you have conversation between characters, you know, you can use the VideoSubFinder to get the text. So that gives you a lot of knowledge about how the game is. In fact, just by getting all the text, in fact, if I can get all this as text, I'm not sure whether the VideoSubFinder can find like left mouse click. Okay, but at least this text I think should be okay. If you can get all the text, you can play quite a lot of the game already. Like a lot of the information is here. Look at this. The game has given you all this. Okay, so again, this is very artificial. In real world, you don't have this pop-up saying I've done this task. This is your next task. You don't have this kind of thing. So I would say Red Dead Redemption 2 actually can be quite simple for AI if you can just read the text. Yeah. So at least for what they did, they extracted the keyframes with the text with VideoSubFinder. Okay, this part is not very clear in the paper, like whether they do it for all frames or keyframes. but I'm just going to take it that they do it for keyframes only because it's very expensive to do for all frames of the video. It's very, very long. The video, each image processing takes a lot of money. So for GPT-4V, I know in the paper what they did is that they only do it on the last frame. So they asked GPT-4V, okay, the game will give you inputs of different UI elements, read out one by one all these lines. So their prompt is like 300 lines long. No, sorry, not 300, like 100 lines long. It's a very long prompt of how to use GPT-4V to tell the image, like read from top to bottom, all this, and then basically write out the different text components. So they'll ask GPT in one prompt to execute all this. I actually didn't see in their code, okay, this is me, okay, I don't know whether I see correctly. I didn't see in their code a cropping and asking GPT-4V to redo the analysis on crops. Yeah, so this part here was used in V-Star. So V-Star realized that if you crop the image and you ask GPT-4V to process, you get more accurate answers. And I tried it myself, it works. Okay, because GPT-4V might use vision transformers, they might lose out on positional information. But if you make it big enough that it can fit inside maybe it can fit inside some patches like that, you might get better resolution. So this might actually improve some performance. But the main thing is, at least from what they test out, the OCR capabilities of using this image is good enough. So GPT-4V will give you the OCR for all the text in the game. All right. But GPT-4V is not great. So they don't really know that the horse is at this position. So if let's say the target is to lead the horse, you need to go to the horse. GPT-4V won't tell you, okay, the horse is at XY coordinate, this one. Nope, GPT-4V is not good at that kind of stuff. Okay, so what they did, okay, they did an augmentation, okay, with GroundingDino. Okay, so with GroundingDino, what they did was that they give because GroundingDino is quite cool actually. What you do is you give some human text, or basically give some text like freeform, and then they will give you bounding boxes for it. So traditional bounding box finding, you need to kind of only find stuff, like for example YOLO, you only find stuff from ImageNet, the categories. But if let's say I were to describe like, oh, I want the leftmost diamond, maybe for this image, GroundingDino would interpret this using transformers, and then it will just bound this diamond here for you. Yeah, so that's quite cool because you can just do any arbitrary boxes. So this GroundingDino over here, in the code, it's not obvious how they did it. Okay, I tried to look through it. The details is not there in the code. Okay, so that is probably what I suppose they did, is that if you have this UI elements here, you could ask GroundingDino to, or GroundingDino to box up for you where the elements are. And then you have your target position already. So you can do this for both the UI elements and the targets. If GPT-4V is good enough, you don't need to do GroundingDino for UI elements. You just need to do for targets. So you know where the horse is. If let's say you need to fight enemies, you know where the wolves are, you can use that to do a bounding box, because GPT-4V is not good at bounding boxes. Okay, you try it yourself, you use GPT-4V, you say, where is this in the image? It's not good at all. It's not good at all. You try it, yeah. So that is something that it's that is something that needs to be improved. So that's why the bounding boxes are used. There's also another thing called icon matcher. So if you look at this mini map over here, there's this little white color arrow here. And this white color arrow is not really well seen because the GPT-4V is not able to go zoom in enough. Or even if you zoom in enough, it cannot identify that's a logo. So what icon matcher does is that you give it a template of maybe the minimap white arrow, and you ask the icon matcher to find all instances of this icon. So like, for example, if I give you this diamond here, you can see that using OpenCV, the multi-template matching is called MTM, old technology. But the idea is you match this icon with all different icons in the image to get the bounding boxes. So you can use that to kind of infer where the direction of the arrow is in the minimap. Or if you have particular UI elements that, this left click that maybe GPT-4V cannot process, you can put that as a template and then ask the template matcher to find out where all the positions of all this. So this augments with more information. So you can see that this is a hack, okay? Because in real life, you know, where, like, how do you know what to look out for? How do you know what icons to match? Okay, maybe you can store the icons in some memory bank. Then yes, that'll be fine. Next time you see like a diamond, you know, okay, I want to find the diamonds. But this is more of a hack because the vision processing module is not able to do those yet. Okay, so you can see that GPT-4V is not good with positions, so they augment with GroundingDino to get positions of more objects. And the icon matcher is also to get more images of the different like minimap arrows and so on. But overall, with all these abstraction spaces, you can get a more complete picture. You can not only get what the whole image can do, like the GPT-4V overall impression of image, you can also use the VideoSubFinder to find the subs. You can also use the GPT-4V to OCR the UI components. You can use GroundingDino to get the bounding box of the objects and icon matcher to get more bounding boxes. It's quite neat actually, because I feel that these augmentations help to mitigate a lot of the flaws of GPT-4V. And this overall helps to make the game knowledge preserved, even though GPT-4V backend, I believe, using vision transformers, it loses a lot of positional information, but this positional information is preserved by this bounding boxes method, like GroundingDino and even icon matcher. And of course, the VideoSubFinder is great for getting the conversation up and getting the keyframes to do this analysis on. Okay, any questions so far for this slide? Okay, so I think that's more or less it for today. So the rest next week I will cover on the reasoning and planning module. That will take one whole session or so because this takes a while, okay, and how to solve it. So there's also extra stuff about how the vision module okay, maybe I just cover the vision module first because the vision module is okay, maybe next week, yeah, because it's already late. So the idea is GPT-4V is not great at localizing stuff. It's even giving you hallucinations of like whole L becomes a W key. Yeah, so these are the stuff that I think these are the problems. If you use just a pre-built language model, it may have a mismatch to the game. So that's it for today. And next week we'll cover the rest of the questions. Okay, so before we end for today, any last comments before I conclude? All right, and yeah, I'll see you all next week then for the rest of the memory action planning, and you know, we will discuss more of how to solve the problems of abstraction spaces. Cool.
All right, awesome. Thanks, John.
All right, see you all next week then. Okay, bye.